We will now use the concepts we developed in connected masses to solve problems. Let's start with this problem. A 10 kilogram box is on a ramp inclined at 37 degrees to the horizontal. What is the maximum force required to pull the box up the plane? What is the force pressing the box onto the plane? What is the normal force applied by the plane on the box? Well, it's a simple application of what we have discussed so far. We have a box that is of mass 10 kilogram on an inclined plane, inclined at an angle 37 degrees with the horizontal. Now, what is the weight of this box? The weight of the box is m times g, that is 10 kilogram times 9.8 meter per second squared, that is 98 Newton. And what is the direction of this weight? It will be acting vertically down. So the weight is 98 Newton acting vertically down. Well, this 98 Newton now has two components. What are they? There is a component mg sine theta. Well, this is mg. So that mg sine theta down the plane and mg cos theta at right angles to the plane. The component of the weight pulling the box down the plane will be mg sine theta, that is 98 sine 37 degrees, that is 59 Newton. So the force pulling the box down the plane is 59 Newton, which is 98 sine 37 degrees. What is the minimum force that is required to pull the box up the plane? Well, the minimum force, what you need to do is to balance this force. The box is being pulled down by a force of 98 sine 37 degrees, that is 59 Newton. So in order to balance that force, you need to apply an equal force up the plane. Then you are ready to move it. Well, some of you would say, but don't you need a bigger force than 59 Newton? Well, remember, if there is a net force, it's going to produce an acceleration. We want the state when the forces are balanced. So, in order to pull the box up the plane without causing acceleration, we need an equal force in the opposite direction. So the amount of force you require to pull the box up the plane is 59 Newton. That is the minimum force you require to pull it up without any acceleration. If the upward force is greater, there will be a net force. That net force will produce an acceleration. So the answer to part A is you need 59 Newton up the plane. B. What is the force pressing the box to the ramp? The box pressing the box to the ramp is this force, the component at right angles, mg cos theta, and that mg cos theta is 98 cos 37 degrees, that is 78.3 Newton. And this is the force pressing the box onto the inclined ramp. What is the C part? What is the normal force applied by the plane on the box? The normal force applied by the plane on the box will be opposite to this 98 cos 37, and that will be exactly equal to that amount of force. All right, let's do another one. a mass 2.25 kilogram on an inclined plane, inclined at an angle theta equal to 37 degrees, is connected by a string that passes over a pulley to a mass of 1.65 kilogram hanging freely. Find the acceleration of the system of masses and the tension on the string. Well, we have now the connected masses on an inclined plane. Let's draw a diagram of that. Here is the inclined plane. The inclined plane is inclined at an angle 37 degrees. The mass 2.5 kilogram on the inclined plane is connected by means of a string to another mass of 1.65 kilogram, and that is hanging freely. Well, we need to figure out the force, the net force on each of these masses. Is that right? That's the method we developed. Isolate each object and figure out the net force on each object. Let's try that. We will assume that 1.6 kilogram mass is moving down, pulling the 2.25 kilogram up the plane. So we will assume that the system is actually moving down. That means the 1.65 kilogram is falling and the 2.25 kilogram is moving up the plane. Let's study the forces acting on the 2.25 kilogram. Now, by now you must be familiar with the forces. What are the forces acting on the 2.25 kilogram? First of all, its weight mg. Mg is, mass is 2.25 kilogram, g is 9.8. Therefore, its weight is 22.1 Newton. That is acting vertically down. The weight of the box is 22.1 Newton acting vertically down. And now, the moment you mark the weight, you must know a component of this weight will be pulling the box down the plane. What is that component? That component is mg sine theta. Mg is 22.1. So 22.1 sine 37 is the force pulling the box down. And then what is the force pressing the box onto the plane? That will be 22.1 cos 37. The force pressing 2.25 kilogram onto the plane is 22.1 cos 37. That is 17.6 Newton. So this force is 17.6 Newton. That will be 22.1 cos 37. It works out to be 17.6 Newton. And the force pulling the 2.25 kilogram down the plane will be 22.1 sine 37 degrees, and that is 13.3 Newton down the plane. Alright, what is the other force? Well, there is a force applied by the plane at right angles, and you can see that will cancel with this force. So you don't need to worry about the forces that are at right angles. What is the other force acting on this? There is a tension on this string which is pulling the box up. So the tension T on the string pulls the mass up the plane. That is the tension T. Tell me, what is now the net force on that 2.25 kilogram mass? You can see the forces at right angles cancel. So only these two forces survive. Therefore, the net force pulling the box up the plane is T minus 13.3. That is the net force. and that net force must be equal to mass times acceleration. So the net force on the 2.25 kilogram is T minus 13.3 Newton. And that net force must be equal to MA, and we have our first equation. What is that first equation? T minus 13.3, that is F net, equal to MA, 2.25 times A, and let's rewrite that equation. That will be T minus 2.25A equal to 13.3. That is our first equation. Now, let's now study the forces acting on the 1.65 kilogram mass. Tell me, what are the forces on this mass? Well, there are two forces on it. Its weight is acting vertically down. What is that weight? Weight mg is 1.65 kilogram times 9.8 meter per second squared. That is 16.2 Newton acting vertically down. That is one force on this mass. What is the other force? The other force is the tension. The tension T is up. And now, the mass is falling, which means what is the net force on that mass? The net force will be 16.2 minus T. So the net force is 16.2 Newton minus T, and this net force must be equal to mass times acceleration. F net equal to MA, the net force equal to 16.2 minus T, M equal to 1.65, A is the acceleration which we need to find. Because they are connected, acceleration of this mass is the same as the acceleration of the other mass. So we have now the equation F net equal to MA, 16.2 minus T equal to 1.65A. Rewrite that equation, what will it look like? It will be T plus 1.65A equal to 16.2. Just move the negative T to the right, and there you are. And you have two equations. T minus 2.25A is 13.3, and T plus 1.65A is 16.2. You can now solve these equations. Actually, if you want to use the calculator, you can use the method I showed you a couple of classes ago. Use a matrix. Use a 2 by 2 matrix for the left side and a 2 by 1 matrix for the right side, and find A inverse multiplied by B, and that will give you the values of T and A. So I'm going to say, solving these equations give T equal to 15 Newton and A equal to 0.7 meter per second squared. Alright? If anybody has any problems solving these equations, let me know. I'm sure you will have no trouble solving those equations. Okay, let's now do another problem. An 80 kilogram block and a 10 kilogram block are connected by a rope that passes over a frictionless peg. This can be referred to as a double inclined plane. It is inclined on the left and inclined on the right. So you have an 8 kilogram mass sitting on the left side of the inclined plane and a 10 kilogram mass sitting on the right side of the inclined plane. Okay, find the acceleration of the block and the tension in the rope. It is not different from the problem we just did. All we need to do is isolate each object and identify the forces acting on each of them. Alright, let's start with this 8 kilogram. Tell me, what do you think is the direction in which the system is going to move? This is a 10 kilogram at 50 degrees. This is an 8 kilogram at 40 degrees. So you would assume that the system moves like this. The 10 kilogram moves down and the 8 kilogram moves up. Well, that is a guideline to write our equations. Alright. First we will study the forces on the 8 kilogram. Can you do that on your own? What is the weight of the 8 kilogram? The weight of the 8 kilogram is its mass times g. 8 kilogram times 9.8 meter per second squared. That is 78.4 Newton, and that will be acting vertically down. Alright, what are the two components of that force? A component of that will be pulling the box down the plane. That will be mg sine theta, 78.4 sine 40 degrees. And the force pressing the block will be mg cos theta. That will be 78.4 cos 40 degrees. Alright. The force pulling the 8 kilogram down the plane is mg sine theta, which is 78.4 sine 40 degrees. That is 50.4 Newton. The force pulling the block down the plane is 50.4 Newton. Now the force pulling the 8 kilogram up the plane is the tension T on the string. So the tension T on the string. Do we need to worry about the forces that are at right angles? We don't need to worry about the force that is pressing the block onto the inclined plane, because that force will cancel with the normal force. They will be equal and opposite. So really we don't need to waste time on those two forces in such a problem. Alright, the force pressing on the surface and the normal force will cancel each other. Therefore, we will not worry about it. As a result, what is the net force on this 8 kilogram? The net force will be the tension T acting up the plane, 50.4 Newton acting down the plane. The net force will be T minus 50.4 Newton. And that net force must be equal to MA. So F net equal to MA, let's write that equation. If this is the net force, T minus 50.4 equal to MA. M is 8 kilogram and A we need to find. So we have one equation which, when you write it in the standard form is the variables on the left, the constant number on the right. So that will be T minus 8A equal to 50.4. We have one equation using the 8 kilogram mass, and we do the same thing for the second mass, and I'm sure you can do that on your own. You may not be able to read what I have on the screen, so you can try that on your own. Let's now study the forces on the 10 kilogram mass. What is the weight of the 10 kilogram mass? The weight will be mg, 10 kilogram times 9.8 meter per second squared. That is 98 Newton acting vertically down. The weight is 98 Newton acting vertically down. Alright, what is the force that is pulling this 10 kilogram down the plane? That will be mg sine theta. That will be 98 sine 50 degrees, and that is 75.1 Newton. That is the force pulling the 10 kilogram down the plane, 75.1 Newton. Now, do we need to consider the forces at right angles? We don't, because they cancel each other. Now, what is the force acting on the 10 kilogram up the rope? The tension T is acting up the plane. There you are. Therefore, what is the net force on the 10 kilogram? Because the 10 kilogram is moving down the plane, the net force is 75.1 minus T. That is the net force on the 10 kilogram. And this net force must be equal to this mass multiplied by the acceleration. So you have a F net equal to MA, 75.1 minus T equal to 10A, and rewrite it in the standard form. We get 10A plus T equal to 75.1. And now you have two equations, T minus 8A equal to 50.4, T plus 10A equal to 75.1. Well, solving that equation is very simple. You don't even need the calculator. Now, look at the way I can do that right here. Subtract the top equation from the bottom equation. That means T minus T equal to 0. T disappears. 10A minus negative 8A will be 18A. And 18A is on the left side. Now 75.1 minus 50.4. So 18A equal to 75.1 minus 50.4, and you can find your A. Alright? This is what I did. T minus T equal to 0. 10A minus negative 8A is 18A equal to 75.1 minus 50.4. And solving that gives you T equal to 61.4 Newton and A equal to 1.4 meter per second squared. Now, these kind of problems are rather simple now, and you must be able to do these kind of problems. Okay, let's look at another problem. A box of mass 3.5 kilogram rests on a frictionless shelf. This is the box of mass 3.5 kilogram resting on a frictionless shelf and is attached by strings to masses M1 equal to 1.5 kilogram and M2 equal to 2.5 kilogram, which hang freely as is shown here. And we ignore friction because we haven't started talking about friction yet. That will be done in the next class. Find the acceleration of each boxes and the tension in each string. Now here there are two pieces of string. A string that connects the top mass with the left mass, that is this. There is a tension T1 on that string, and the second string connects the 3 kilogram mass to the 2.5 kilogram mass, and the tension on that string is T2. That means there are going to be 3 variables here and 3 equations. Okay. The net force on M1. Let's talk about M1, this mass. What is the net force on this M1? The weight M1G is acting down the plane. The tension T1 is acting up. And we would assume that the system moves from left to right. That means the net force on M1 is T1 minus M1G. Now, what is M1? M1 is 1.5 kilogram. and therefore its weight m1g is 1.5 times 9.8, that is 14.7. So T1 minus 14.7 is the net force on M1. What is the net force on M2? The weight of M2 will be M2G, which is 2.5 kilogram times 9.8, that is 24.5 Newton. That is the weight pulling it down, and the tension T2 is pulling it up. So what is the net force on M2? The net force on M2 will be 24.5 Newton minus T2. Well, before we do that, let's write down the equation for M1. The net force on M1, T1 minus 14.7 equal to M1A. So T1 minus 14.7 equal to 1.5A. That is the equation for the mass M1. Now remember, the easiest way to solve problems like this, as I told you, is isolate each object and find the net force on each of them. Alright, similarly for mass M2, can you write an equation like this straight away? You can look at this and write it straight away. You say 24.5 minus T2 equal to M2A, 2.5A. There you are. 24.5 minus T2 equal to 2.5A. I don't think it needs a lot of explanation. How about the mass M3? Can you write an equation for that? What is the net force on M3? The tension T2 is pulling it to the right. The tension T1 is pulling it to the left. And since the system is moving to the right that way, we say the net force is T2 minus T1. So T2 minus T1, the net force equal to MA, 3.5A. So T2 minus T1 equal to 3.5A. We have three equations, and you can solve for these three equations. And in order to solve these, you need to rearrange them. Now look at the way I'm going to rearrange them. T1 plus 0 T2. Remember, we have three variables, and each equation must contain all the three variables if you want to use your calculator to do that. So I want you to solve these equations on the calculator. So our first equation is T1 plus 0 T2 minus 1.5A equal to 14.7. In other words, we write the variables all on one side and the number to the right side. I hope you understand that equation. T1 plus 0 T2 minus 1.5A equal to 14.7. Alright, how will you write this equation? There is no T1 there, so there will be a 0 T1, alright, minus T2 minus 2.5A equal to negative 24.5. Or you can write it like this: 0 T1 plus T2 plus 2.5A equal to 24.5. That's how I have written it here. What I did is left the 24.5 on the left, take the negative T2 to the right. So I have 0 T1 plus T2 plus 2.5A equal to 24.5. Now look at the way I wrote the equation. All T1s must be the first variable, all T2s the second variable, the A is the third variable, all the constant numbers on the right. Alright, how will we write this one? Now look at the way I wrote this one. Now what I did is I took both these variables to the right. So a negative t1 comes to the right, becomes positive t1. t2 comes to the right, becomes negative t2. And 3.5a is sitting there, plus 3.5a, and the left side is 0. So this equation is t1 minus t2 plus 3.5a equal to 0. Alright, how would you solve these three equations on your calculator? Well, make a matrix which is a 3 by 3 matrix. Make a 3 by 3 matrix and enter the coefficients. What is that? 1, 0, negative 1.5, that's the first row. 0, 1, 2.5, that is the second row. 1, negative 1, 3.5, that is the third row. So you got your matrix A with those numbers. And your matrix B will be a 3 by 3 matrix. Alright? And make your matrix B and calculate A inverse multiplied by B. I'm going to show this one more time to you how to make these matrices. Go to matrix second x inverse, or turn on the calculator first. Well, go to matrix second x inverse is your matrix. Go to edit. Well, edit matrix A. There you are. And that has to be a 3 by 3 matrix. So what do? Type in 3, enter, 3, enter. And now type in all those values. What are the coefficients on the left side? Now look at your equation. That will be 1, enter, 0, enter, negative 1.5, enter. The second equation, the coefficients are 0, enter, 1, enter, 2.5, enter. The third equation is 1, enter, negative 1, enter, 3.5, enter. You have your matrix A now. Let's go and make our matrix B. Matrix B, let's go second x inverse and go to edit, 2 places to the right and 1 down, matrix B. Matrix B is going to be a 3 by 1 matrix. 3, enter, 1, enter, and write down the values on the right side. What are they? 14.7, enter, 24.5, enter, 0, enter. So you got 14.7. I think I have the second one is 24.5 and the third is 0. And once you have those values entered, quit the screen and go and collect your matrix A. How? Second matrix, collect A. Simply enter and take the inverse of it. A inverse multiplied by matrix B, second matrix, and select B, come down, and you have A inverse B gives you the first variable is T1, the second variable is T2, and the third variable is the acceleration. So T1 equal to 16.6, T2 is 21.23 and the acceleration A is 1.31. All right, I think now we will now talk about the weight of a person moving in an elevator. Now, have you experienced when you are in an elevator and suddenly the elevator picks up acceleration upward and your knees bend? Now, have you experienced that? What is the reason? The reason is the elevator suddenly applies an extra force upward. You see, before the elevator moves, your weight mg is acting vertically down, and the elevator applies the normal force upward. They are equal and opposite. When the elevator wants to accelerate upward, there must be a net force upward. And what will be therefore the total force upward? It will be mg plus ma, the force needed to produce that acceleration. And that means you will be pressing, or the elevator floor will be pressing on you harder. It means if you are standing on a weighing machine, you will weigh more. Why? Because the elevator floor will be pressing harder. That means you will be pressing harder on the weighing machine. You will feel heavier. On the other hand, if the elevator is accelerating downward, you feel as though something is moving, giving way from your feet. You feel weightless. All right, let's talk about that. When you stand inside a stationary elevator, you press the floor of the elevator with your weight. There you are in the elevator. Well, this is the elevator moving up, this is the elevator moving down. I haven't got where the elevator is stationary. Now, if the elevator is stationary, the floor of the elevator presses you upward with the same force. That means if you are standing on a weighing machine on the floor of the elevator, which is not moving, it will read your actual weight. Now, if you stand on a weighing machine, that will read mg, your actual weight, because that is the force pressing onto the elevator floor. If the elevator now moves up with an acceleration a, the floor of the elevator will push you up with an additional force ma. You see, before it started accelerating, the floor applied a force equal to mg, so that there is no net force on you. Now, the elevator wants to produce an acceleration on you upward. That means it must produce an additional force on you. So what is the force now the elevator applying on you? Is mg plus ma. And you in turn will press the elevator floor back with the same force. That means your weight will now be greater. So the scale will now read mg plus ma. So here you can see the elevator is accelerating up and you are buckling down. Well, I'm exaggerating though. But you are pressing onto the floor of the elevator with a greater force. That is mg plus ma. You will feel heavier. On the other hand, if the elevator moves down with an acceleration, then the force ma will be downward. That means the floor of the elevator will press on you with the force mg minus ma, and that will be therefore what the scale will read. You will feel weightless. So, how do you want, if you want to lose weight, therefore what do? There is no need for any dieting. You can go to an elevator and make the elevator go down with an acceleration. Your weight as is read by the machine will be mg minus ma. Well, what happens if the elevator cable breaks and the elevator falls freely? If the elevator begins to fall, will you be pressing onto the elevator floor at all? Well, if you are now on the elevator floor, the floor is falling, you are falling, you are not pressing on the elevator. What will the machine, the weighing machine, read? 0. You will be weightless. So you are falling freely, the elevator floor is falling freely. That means anything that falls freely will be weightless. That's right. If you want to lose all your weight, all you need to do is go to the top of a big building, jump down. During the time you are falling freely, you are weightless. That's right. Now, let me see if I can demonstrate with this machine here. Well, this is a spring balance, a scale. Now, this is the elevator at rest. It reads the actual weight. Now, suddenly, if I move up, now can you see what happened? Suddenly, if I move, this comes down. As it comes down, it is moving, it is reading more. You can see the moment I move up, the weight increases. And if I fall, the reading decreases. If I let it go, you can see the reading is 0. While falling freely, this will read 0. So the weight of a freely falling object is 0. That means if the elevator is accelerating upward, your weight as is read by the weighing machine will be mg plus ma. If it is moving down, the weighing machine will read mg minus ma. And if the cable breaks, there you are weightless. That's right, you can fly around inside the elevator. Let's do a problem. A 70 kilogram person stands on a scale in an elevator. What is the weight? What weight in Newton does the scale read if the elevator is at rest? Well, if it is at rest, it will read his actual weight. Be moving up with an acceleration of 0.525 meter per second squared. What will the elevator read? What will the weighing machine read? It will be mg plus ma. If it is moving down with an acceleration, it will read mg minus ma. So part A, when the elevator is at rest, the scale will read the actual weight mg, that will be 686 Newton. And if the elevator is moving up with an acceleration a, the scale will read mg plus ma. mg plus ma, that is, this is mg plus m times a, that will be 722.75 Newton. Now, have you heard of people who go in spaceship talking about experiencing 2 Gs and 3 Gs and so on? What does that mean? If a rocket suddenly takes off with a tremendous acceleration, you know, when it takes off with a sudden acceleration, the seat will be pressing onto you so hard, you get crushed onto that seat. Your weight will be mg plus ma. If that acceleration is 3 times the acceleration due to gravity, you are experiencing 3 Gs. And that needs a lot of experience, otherwise your whole system will get crushed. On the other hand, if the rocket is falling freely, have you seen in air shows the plane coming diving down? That time you experience weightlessness. While the plane is climbing up, you will experience 2 Gs and 3 Gs. You are getting stuck onto the seat with a tremendous force. Well, so when the elevator moves up with an acceleration a, the scale will read mg plus ma, that is 722.75 Newton. When the elevator moves down, well, this must read move down. Okay. When the elevator moves down, what is the situation? This must be corrected to down. The scale will read mg minus ma, and that will be 649.25 Newton. Okay, let's do another one. A man stands on a scale in an elevator that has an upward acceleration a. The scale reads 960 Newton. When he picks up a 20 kilogram box, the scale reads 1200 Newton. Find the mass of the man, his weight, and the acceleration. Okay, that's a good problem. Let's set it up. Let the mass of the man be m kilogram. That is what we need to find. The scale reading when the elevator is accelerating up with an acceleration a is mg plus ma. Is that right? Yes. That means 960, this is the reading of the scale, that 960 equal to mg plus ma, 9.8 m plus ma. We need to find m and we need to find the acceleration. Now, that means we need one more equation, is that right? Alright, well, one more equation can be obtained when the man picks up the 20 kilogram box. What happens? When he picks up a 20 kilogram box, the scale reads 1200 Newton. That means this m now becomes m plus 20, and then the scale reads 1200. Well, if you want, let's solve the first equation for a. A equal to 960 minus 9.8 m over m. Well, and that will be 960 over m minus 9.8 m over m, and this is now an equation for A. When he picks up a 20 kilogram box, the total mass now is, this m becomes m plus 20, and then the scale reading becomes 1200. So the scale reading becomes 1200, m becomes m plus 20. We have 1200 equal to 9.8 times m plus 20 plus m plus 20a. And what I'm going to do is replace this a. I'm using a substitution method here. You see, I have used the first equation to solve for a, and I'm going to substitute this a by that value. So a is 960 over m minus 9.8. Now, this is our equation. That will be 1200 equal to, what I have done here is, if you want to watch there, I took m plus 20 as the common factor. Do you understand that? If you put m plus 20 as the common factor, what is left in here will be 9.8. Plus, what is left here is 900 over 60 over m minus 9.8. You see, that is a neat way to do that, because you notice that inside here 9.8 minus 9.8 will cancel. Alright, did you see what I did? I factored out m plus 20, and the remaining is this. And that gives me 1200 equal to m plus 20. I took this, cancelled the 9.8 and negative 9.8, took this m and put it under here. M plus 20 over m times 960. And now I got an equation in terms of m alone. I can solve it. Now that will be multiply both sides by m. When you multiply both sides by m, on the right side m will cancel. The left side you have 1200m equal to 960m. Distribute that 960. 960m plus 960 times 20, that is 19,200. And you know how to solve this now. M equal to 80 kilogram. Now, I was just showing you one method of solving this equation. Actually, those two equations are systems of equations. You can simplify them the same way we have been solving other systems of equations. Alright? So, it's not a big difficult thing. Now, once you have m, we can go and calculate the acceleration. Acceleration we have obtained as 960 over m minus 9.8, and using the value of m, we get acceleration equal to 2.2 meter per second squared. That was a good problem. Try and do this on your own. Well, I think we have done quite a bit of explanations on connected masses, and we solved problems using it. Now remember, we are going to do almost the same type of problems in the next section. So you must be familiar with all these skills in this section. Alright, I'll see you for lesson 3 later on in this unit.